Today, we're going to completely shatter the myth that programming is just for software developers. We're going to prove exactly why Python has evolved into an absolute necessity. Honestly, a true superpower for every single engineering discipline out there. Whether you are designing structural gantries, optimizing fluid dynamics, or planning the future of our electrical grids, the days of the old wrenches and calculators only approach are officially dead.
Okay, let's dive right into the core problem. Take a second and really think about your daily workflow. Are you still copying and pasting values from an Excel sheet into a CAD model? Are you spending hours just pointing and clicking through endless graphical menus in commercial simulation packages, all just to extract a single peak stress value? Or maybe you're waiting for a machine to break to perform reactive maintenance. If you're doing any of this, you are severely falling behind.
The reality is, there's a massive workflow shift happening right now across the entire industry. We are moving away from the old manual data extraction method, which takes hours and just begs for human error, to the Python way. And the Python way is all about instant automated calculation and execution in mere seconds. You can literally command your computer to loop through an entire folder of files, isolate specific timeframes, filter out the noise, and save beautifully organized summary sheets, all without a single mouse click. Now, when you first bring Python into your engineering tasks, your immediate superpower is usually the Pandas library. Pandas treats data tables as data frames stored directly in your computer's memory. This completely bypasses the visual rendering bottlenecks you get with traditional spreadsheet software. To put that into perspective, you can process and analyze 1,000,000 rows of data in under 2 seconds. The sheer speed is an absolute game changer. But it's not just pandas, right? There is a vast ecosystem of open source libraries that act as the bedrock for all this automation. You've got NumPy and SciPy handling high-speed numerical computing and complex scientific calculations, way better than messy formula sheets. Matplotlib totally automates your data visualizations, and SymPy allows you to do symbolic mathematics, meaning you can solve and simplify complex algebraic equations perfectly before you even plug in the numbers. Together, these libraries shift your productivity into absolute overdrive. All right, let's look at mechanical engineering, specifically automating CFD, FEA, and CNC manufacturing. To see how this translates to a real-world mechanical automation, just take a look at this workflow. Instead of manually clicking through CAD programs like SolidWorks or finite element analysis tools like ANSYS, Python acts like a puppet master behind the scenes. Using direct APIs, a Python script can flawlessly run this entire 4-step workflow in the background. It reads your design table, auto-updates dimension variables like flange heights, rebuilds the whole model, loops through 50 result databases to extract peak stress values, and then uses libraries like ReportLab to automatically generate a compiled professional PDF report. And Python's capabilities seamlessly extend right into fluid dynamics. By combining Python with software like Helix, engineers can systematically analyze, build, and refine routine computational fluid dynamics workflows. This transforms all those repetitive setup and mesh generation tasks into standardized best practices, which radically increases your simulation agility and drops overhead costs. Plus, it doesn't stop at simulation. Python actually controls physical manufacturing too. When you use a CNC mill or an industrial 3D printer, the machine reads G-code. And because G-code is basically just plain text, Python can seamlessly parse those massive coordinate files. Let's say you want to prevent machine vibration. You can just write a script to automatically inject modified speed commands exactly when the toolpath hits a sharp corner. Doing that line by line manually would be literally impossible, but Python handles it instantly. Moving on to civil engineering, let's explore voice command structural analysis AI. This is where things get really wild. Python isn't just automating clicks anymore. It is completely revolutionizing how we interact with our tools. Researchers recently integrated the Python library Anastruct, which is specifically designed for 2D structural analysis using matrix methods, with a speech recognition library. This means civil engineers can literally speak to their computers, and the script seamlessly translates as voice commands directly into Python matrix formulations to define columns, beams, constraints, and structural loads. To prove how well this actually works, check out this real-world case study of the Nuestra Señora de las Mercedes School Pavilion in Peru. You can see the applied loads on the structure. We've got a 1.5 kilonewton per meter leeward load and a 2 kilonewton per meter windward load, and these loads were mapped and generated perfectly onto the framework using entirely automated voice commands, no typing required. And it gets better. The Python algorithm automatically computes the intricate numbering of the entire structure. We're looking at a 3-story, 7-span gantry composed of standard HEA 240 and IPE 270 metal profiles. The script mapped out every single node and element for analysis, without the engineer needing to execute a single manual click inside traditional structural software.
Once you finish your voice commands, boom, the script instantaneously outputs the finite element results. You can easily capture maximum base reactions, like the one peaking at 34.23 kilonewtons here, alongside precise shear and axial force diagrams. And just like in our mechanical engineering example earlier, Python can export these detailed results directly into a finalized PDF report in a matter of seconds.
Next up is electrical engineering. Let's talk about power system simulation with PSA.
When you need to tackle multi-period energy grid simulations on a massive continental scale, engineers turn to the free PSPSA toolbox. It uses core network components like buses, loads, generators, and links. What's absolutely brilliant here is the link component, because it allows for sector coupling. That means Python can simulate not just electricity, but how the power grid interacts with gas, heating, and transport networks. This optimizes operational investment for modern energy systems that have high shares of variable renewables.
To actually manage these grids on a European scale, using open datasets like SciGrid and GridKit, PSAPI just churns through massive mathematical processes. It simulates full nonlinear alternating current load flows and linearized direct current network equations. It even uses advanced algorithms like k-means clustering to sort of bundle mathematical nodes together while preserving crucial transmission lines. This makes it possible to run these huge multi-period optimizations over vast geographic areas without crashing your computer.
Finally, let's hit computer science engineering, AI, machine learning, and IoT integration. Here is where Python acts as the ultimate bridge, unifying all these modern, data-driven physical systems. By integrating machine learning libraries, Python is driving a massive shift away from costly reactive maintenance, where a factory loses thousands of dollars an hour waiting for an unexpected failure, to highly efficient IoT-driven predictive maintenance. Using sensors and Python's data analysis, algorithms can actually forecast system failures before they happen. So, bringing all of this together, what's the actual bottom line ROI for an engineer who adopts this superpower? Well, going back to that civil engineering voice command study we looked at, researchers documented an astonishing efficiency gain of up to 94.29%. Think about that. A structural analysis workflow that traditionally took an average of 30 minutes in graphical software was reduced to exactly 2 minutes using Python automation. And I think that brilliantly hits the nail on the head. Python is clearly no longer just a nice-to-have skill. It has permanently automated the engineering world, which leaves us with one critical question regarding the trajectory of your technical career. With automation moving this incredibly fast, is your skill set truly future-proof? Thank you for joining me for this explainer, and I really hope this sparks some new ideas